Hello everyone, my name is Ajay Mirzi. In this presentation, I am going to discuss about my tech talk topic wall temperature effects on hypersonic aerodynamics of the Mars entry capsule. Abstract. The chemical non-equilibrium method is implemented to investigate wall temperature effects on the hypersonic aerodynamics of the Mars entry capsule named Mars Science Laboratory. Two isothermal walls ranges from 1000 Kelvin and 2000 Kelvin, and a reactive equilibrium wall temperatures are used to take account of the temperature effects respectively. The numerical results show that the wall temperature has no significant effect on the pressure of the forebody, while influences the pressure of the afterbody remarkably, especially at the separation area. The shear stress of the forebody increases with the wall temperature increased, and the wall temperature affects the shear stress of the afterbody obviously. The wall temperature has no significant effects on the aerodynamics of the forebody. At different wall temperatures, the maximum discrepancy of the forebody's axial force coefficient, normal force coefficient, and pitch moment coefficient is merely 0.05%, 1% and 1.2 respectively. The wall temperature impacts the aerodynamics of the afterbody significantly. At different wall temperatures, the maximum discrepancy of axial force coefficient, normal force coefficient, and pitch moment coefficient of the afterbody is 55.7%, 26.4% and 61.5% respectively. Introduction. Mars exploration is of great importance for studying evolution of the Earth's environment and future human settlements. In order to achieve the capsule's effective control and precise landing performance, it is extremely essential to accurately predict the hypersonic aerodynamic forces during the Mars entry period. So far, much effort has been paid on this problem. Calculated the hypersonic aerodynamic forces to the Mars pathfinder with thermochemical non-equilibrium models and perfect gas model with specified effective specific heat ratio respectively. An isothermal wall is assumed for the calculation. Devenkeno stimulated the supersonic and hypersonic aerodynamic forces of the MSL by employing the chemical non-equilibrium method and reactive equilibrium wall temperature. Young et al. Studied the hypersonic aerodynamics of MSL with a reactive equilibrium wall temperature. The position of mass center, the ratio of L by D, and the static stability are then investigated in detail. LV et al. Carried out numerical stimulation on the aerodynamic performance of the MSL using chemical non-equilibrium method with component 5 reaction and isothermal walls 700 Kelvin conditions, and the effects of CO2 environment, free stream density, and temperature on aerodynamic performance are then examined. However, there are relatively few studies on the wall temperature effects on hypersonic aerodynamics of the Mars entry capsule, and the selection criteria of wall's temperature are inconclusive and need further studies. In this presentation, the chemical non-equilibrium method is employed to study the effects of wall temperature on the hypersonic aerodynamic characteristics of the Mars capsule MSL. Two isothermal walls 1000 and 2000 Kelvin and a reactive equilibrium wall temperature are used to take account of the temperature effects respectively. Numerical methods. In this presentation, three-dimensional Navier-Stokes equation with chemical non-equilibrium process are solved by finite volume method on structured meshes. A chemical kinetic model of Martian atmosphere including 8 species CO2, CO, N2, O2, NO, C, NO and 14 chemical reactions is implemented. The viscosity and thermal conductivity coefficient are calculated by the binary collision integral model. Diffusion coefficient is calculated using two-component diffusion model. The inviscid fluxes are computed using rho upwind scheme with second order MUSCL reconstruction and min mod limiter. The viscous fluxes are calculated by second order central difference scheme. The implicit lower upper symmetric gas scheme is employed for time integration. Non-slip wall boundary condition is implemented in this study. Computational details. The geometry of the Mars-centric capsule MSL is illustrated in figure 1. The meshes of the solid wall and symmetric plane are displayed in figure 2. The total number of volume grids is nearly 1.21 millions. The cell Reynolds number near the surface is RE 15 into delta is equal to 50. A series of flight conditions on the entry trajectory is chosen in this presentation. All free streams parameters are listed in table 1. Here the table 1 free stream parameters like Mach number, density, temperature and area mass fraction. A fixed surface emissivity of 0.89 is used for all solutions. Besides two isothermal walls, 1000 and 2000 Kelvin are also employed in this study. Due to the lack of related experiments, numerical stimulation is employed to study wall temperature effects on the hypersonic aerodynamics of the Mars capsule. In this figure, a mesh of symmetry and wall surface of Mars surface vehicle. Here we go. We are able to see this meshing, which is done in software for better understanding. Here the table 1 describes the free stream parameters. Result and discussion. Hypersonic flow field. Comparison on the hypersonic flow field is essential to understand the surface condition and the subsequent aerodynamic characteristics. The flow structure is shown in figure 3. In the case of MA set as 24.7 and reductive equilibrium wall temperature is employed. Due to the strong compressible effects of hypersonic flow, the bow shock is near the capsule. After the shoulder, the flow begins to expand. Effects of wall temperature and pressure and shear distribution. In this section, detailed investigations are performed on the effects of wall temperature on pressure and shear stress distribution. In this case, MA is set as 24.7 as seen in figure 4. The wall temperature has negligible effect on the pressure of forebody, while it obviously affects the afterbody where the complicated physical phenomena including the flow separations occur. The difference in afterbody's attachment flow regions is little, and in separation regions it becomes large. The shear stress distribution is presented in figure 4c D. The trends of shear stress is similar at the forebody, though slight increase can be observed with the wall temperature increase. Significant difference occur in the afterbody. At different wall temperatures due to the recirculating flow regions generated, the trends of shear stress differ from each other remarkably. The maximum shear stress of the 1000 Kelvin, 2000 Kelvin and reductive equilibrium wall temperature case is approximately 13, 25 and 18 Pascal respectively. Effects of wall temperature and force coefficient. In this section, due to no side slip, attentions are only focused on the wall temperature effects on force coefficients including axial force coefficient, normal force coefficient and pitching moment coefficients. In this presentation, relative discipline is first defined as maximum minimum. In this figure they are showing axial force, normal force and pitching moments coefficient. Conclusion. In this presentation, chemical non-equilibrium method is implemented to investigate the wall temperature effects on the hypersonic aerodynamics of the Mars capsule MSL. Main findings are as follows. First one, the wall temperature has no significant effect on the pressure of the forebody, while influence the pressure of the afterbody remarkably, especially at the separation area. The shear stress of the forebody increases with the wall temperature increased, and the wall temperature affects the shear stress of the afterbody significantly. Second one, the wall temperature has no significant effect on the aerodynamics of the forebody. At different wall temperatures, the maximum discrepancy of the forebody axial force coefficient, normal force coefficient and pitch moment coefficient is merely 0.05%, 1% and 1.2 respectively. The wall temperature impacts the aerodynamics of the afterbody significantly. At different wall temperatures, the maximum discrepancy of axial force coefficient, normal force coefficient and pitch moment coefficient afterbody is 55.7%, 26.4% and 61.5% respectively.